Hello everyone, how are you all? I hope you all are well. So welcome back. Today we are going to continue our topic, that is solution. Now in the previous video we have already discussed so many things about solution. So if you haven't seen that video, just click on the I button and just see that video, because we are going to continue from there only. So today we are going to discuss another important topic of the chapter solution, that is vapor pressure. Now what is this vapor pressure? Because on the basis of that vapor pressure we are going to discuss a very important law, that is known as Raoult's law. So first of all, what is this vapor pressure all about? We are going to discuss that. Now for vapor pressure I can explain you with the example. Suppose this is our container, okay, any container we can take, okay, or any beaker we can take, and in this container suppose any liquid is present, any liquid which must be volatile. That is very important. So a volatile liquid is present here, and suppose in this volatile liquid we are providing some heat, okay. So we are heating basically this kind of a liquid. Now when we are going to start heating, suppose this liquid we are considering as water, then what is going to happen? The molecules which are at the bottom of the container, first they are going to get that heat, and these molecules will start moving at the surface of the liquid, okay, because as it is volatile means which can be evaporated. So the vapors of that liquid which is placed in this container will start moving toward the surface of the liquid, and they will move to the surface of the liquid and get collected over here like this, suppose. And then what is going to happen? They will start exerting a kind of a pressure on the surface of the liquid, okay. They will be exerting a kind of a pressure, we can say, on the surface of the liquid. So when they are going to exert the pressure on the surface of the liquid, that pressure is known as vapor pressure, okay. So this pressure which is applied by the vapors of the same liquid on the surface of the liquid is known as vapor pressure, okay. So you understand, this is a beaker, we have placed a volatile liquid. Volatile liquid means the liquid which can be evaporated. So in such kind of a liquid the vapors will form. The molecules which are going at the bottom of the beaker will be getting the energy first, okay, and then they will move to the surface, and then they applied pressure on the surface of the liquid, and that pressure which is applied on the surface of the liquid is known as vapor pressure, okay. So our Raoult's law is based on this vapor pressure only, okay. Now what is this Raoult's law? Raoult's law states that in a case of a solution, if any solution is there, the vapor pressure or the pressure of the component is directly proportional to its mole fraction, okay, but it is for the liquid. Now how? I explain you first, then you can understand. Suppose we have two liquids with us. This is liquid A, this is liquid B, okay, and when they are in pure state, like this is their pure state, okay, both are liquid, and one more important thing, that both liquid are volatile, means can be evaporated. Suppose as B component I always considered it as solute. So suppose this is our solute and this is our solvent. So when they are in their original state means they are in the pure state, they must be having some kind of a vapor pressure, because they are volatile, so they must be having some vapor pressure. So their vapor pressure in the original state will be denoted as P naught A, okay. So what is this P naught A? The vapor pressure in pure state, okay, when the state is pure. Same is here, that is the vapor pressure of P naught B is P naught B for the component B, because that B component is also volatile, so it must be also having some kind of vapor pressure. So P naught B will be the vapor pressure in pure state. Okay. Now if you mix these two, that is solute in solvent, then what we are going to get? We'll be getting a solution. Okay, solution. So when you are going to make a solution, now the pressure of the two component will be present in the solution, that is the vapor pressure of component A, that is solvent, and vapor pressure of component B, which is solute. You understand? That is, now the solution which is prepared will be having the vapor pressure of both component. So in such case, when the solution is prepared, now the vapor pressure of each component cannot be in their pure state. Suppose if we are talking about solvent, then solvent vapor pressure will be denoted as PA. Okay, and suppose we have another component, solute, so its vapor pressure in solution phase when the solution is made is PB. Okay, so you understand, when they are in their pure state, their vapor pressure is P naught A and P naught B, but when you prepared the solution, their pressure is denoted by PA or PB. So what RAOULT'S law states, actually the RAOULT'S law is based on the solution which is made of liquid and liquid component. So according to RAOULT'S law, the vapor pressure of a component, that is maybe solute, maybe solvent, is proportional to its mole fraction in that solution. Okay, that is PA is proportional to XA and PB is proportional to XB. Okay, that is vapor pressure of solvent is proportional to its mole fraction and vapor pressure of solute is proportional to its mole fraction. Okay, so that is RAOULT'S law. That is, RAOULT'S law states that in case of a liquid-liquid solution, the vapor pressure of the component is directly proportional to its mole fraction. It's look like similar to the Henry's law, but in Henry's law we were talking about the gaseous solute in the liquid phase, but here both the component are in the liquid phase. Okay, and we are talking about the vapor pressure of them, because in the liquid state they will be turning into the form of a vapor. They can turn into the form of vapor as they are volatile. So that is RAOULT'S law. Now we are going to further see that how this relationship is going to be maintained when two components are mixed together and how the total pressure of the solution we can measure. So let's see. Now as we know, according to the RAOULT'S law, the vapor pressure of a component is proportional to its mole fraction, as you can see. So when you remove the sign of proportionality, here the constant which we are going to use is P naught A. Okay, now what is this P naught A? Already I have explained that the vapor pressure of a component, that is here in the case of the solvent, the vapor pressure of the solvent in the pure state. So here this we can consider as a constant, because the vapor pressure of a pure component will remain constant for a certain component. So PA will be equivalent to P naught A XA, and similarly the PB, that is the vapor pressure of a solute component in a solution, it is also proportional to its mole fraction. So we can consider it as P naught B XB. Okay, that is the vapor pressure of solute in pure state. So that is considered here as a constant. Now if we have to calculate the total pressure of solution, suppose you have to, because these vapor pressures which we have find, that is the vapor pressure of an individual component. Now we have to find the total pressure of the solution because we have prepared the solution. So the total pressure of the solution will be equivalent to the sum of individual pressure of each component, that is PA plus PB, or total pressure of the solution we can denote as PSOL, suppose. Then in that case the PSOL will be equivalent to PA plus PB, or we can say that total pressure of a solution will be equivalent to, if we put these values here, that is P naught A XA plus P naught B XB. Okay, so that is how we can calculate the vapor pressure of the solution. Now suppose this is our equation number 1. We know one more thing, that XA plus XB is always coming equivalent to 1. Okay, XA plus XB is always equivalent to 1, that is the mole fraction of any two component in a solution is equivalent to 1. Then in such case XA can be written as 1 minus XB, okay, or else XB can be written as 1 minus XA. So either of these values if you can put in this equation, suppose we consider them as 2. So if you are putting the equation 2 in 1, suppose I am using XB equivalent to XA equivalent to 1 minus XB, then in such case the total pressure of the solution will be equivalent to P naught A. In place of XA it will come 1 minus XB plus P naught B XB. Okay, so what it shows, if you know the mole fraction of any one component, suppose I know only the mole fraction of the solute, that whatever the amount of the solute I have added in a solution, then also we can calculate the vapor pressure of the solution, that is the total vapor pressure of the solution, using this relationship. Okay, so that is our Raoult's law. Okay, so what was Raoult's law? That Raoult's law states that whenever the liquid solution is prepared, then the vapor pressure of each component is proportional to its mole fraction. So when you remove the sign of proportionality, then the constant which is going to be used is the vapor pressure of same component in their pure state, which is denoted as P naught A or P naught B as solvent and solute. Then total pressure of solution you can calculate by using the relationship by taking the sum of individual pressure, and that is how the equation is made. If you know the mole fraction of any one of the component, then you can calculate the vapor pressure of whole solution. Okay, so that is about Raoult's law. Now important thing is that Raoult's law, one more thing, that Raoult's law and Henry law look like similar, only the difference which you must know, that there is a difference in the constant. In case of the Henry law, the constant we use is KH, okay, Henry's constant, because that is the solution prepared by using gas in the liquid. Okay, and here the constant is the vapor pressure of a component in pure state, that is P naught A or P naught B, because here the solution is prepared by using both the component as a liquid. Okay, so that is the difference between the Raoult's law and the Henry's law. Okay, one more thing. Now this Raoult's law is applicable, okay, this Raoult's law is applicable only for ideal solution. Okay, Raoult's law is applicable only for ideal solution. Now what is this ideal solution? Let's see. So let's see students, what is this ideal solution? So one basic thing, that ideal solution is a type of the solution which totally obeys Raoult's law. Okay, the solution which obey totally the Raoult's law is an ideal solution. Now what is this ideal solution? Basically, what are the things or what are the properties of this ideal solution that we need to see? But first we need to understand that, like suppose already I told you that suppose we have two components, that is A and that is another one B. Okay, now these two components, the component A, which is our solvent, and the another component is B, which is solute. Okay, so they are in this state, that is in their pure state. Now in pure state, important is that what kind of the interaction they are having. Interaction, basically I want to say that what kind of the particles are present when they are in their pure state, like B or A, what type of the interaction is present in them. In such case, in component A, the interaction will be of kind AA, means the molecules of similar kind like AA will be present together. Okay, while in case of the B, the interaction will be of type BB. Okay, that is BB components are going to be together. Now important thing is when you prepare a solution by using this kind of the component, that is A and B, that is now solution is prepared. So a new kind of interaction will arise, because when they are in pure state it is A and B. But when they interact each other and they form a new kind of a solution, so the interaction will be of type AB is now going to be present. Okay. So what ideal solution says that the interaction strength, okay, the interaction strength of AA or BB is going to be equivalent to AB. It means the new solution which is prepared will be having the similar kind of interaction, will be having a same strength interaction which A or B will be having in their pure state. It means the solution will be also having the same strength of interaction. So if that is going to be same, then such kind of a solution is states to be a ideal solution. Okay. So solution which is having the similar kind of interaction as the component which are having in their pure state is said to be the ideal solution. So that is our first point, that what is ideal solution is. Then a very important second point also. Second point states that if you prepare the two solution, then there must be an enthalpy change. You know that whenever we perform some reaction, usually some enthalpy change is there. Maybe the heat is evolved during the process or heat is given out, okay, absorbed. So in such case there may be some enthalpy change. But what is going to happen in case of the ideal solution? The enthalpy of mixing, that is for preparing the solution, is always coming equivalent to 0. It means whatever the energy is there before the process and after the preparation of solution, that is going to be same. So there is no change in enthalpy in case of ideal solution. It means when ideal solution is prepared, there will be no enthalpy change. That is the second point. Then comes the third point, that is the change in the volume. It means when you are preparing the two solution and the solution which is obtained after preparing that, then the change in volume of mixing is also going to be 0. It means there will be no change in volume find when you prepare the solution using the solute solvent. So the volume of mixing, that is the change in volume of mixing, is always going to be equivalent to 0. Okay, that is there will be no change in volume. Volume will always remain same. So these are the 3 points. If these 3 points are followed by any solution, then such solution is stated to be a ideal solution. That is, interaction strength remains same, enthalpy of mixing will be 0, and change in enthalpy and change in volume of mixing is also 0. So that is our ideal solution, and RAOULT'S ideal solution always obey RAOULT'S law. Now there is a graph for the ideal solution to show how the vapor pressure is going to be vary. So that I am going to show you. Suppose this is a kind of a graph which we are going to show. Suppose here our one component XA is there and XB is also there. Now this is the initial point where one component is present in the more quantity and other component may not be present also. So suppose we considered XA here as 1, okay, and XB in such case will be automatically going to be 0. It means that when you move further, the amount of XA will decrease and XB is going to be increase. Okay, so when you move horizontal axis, then XA is going to be now decrease and XB is now going to be increase. So at this point we considered that XA becomes 0, then automatically the XB will become 1 because XA plus XB is equivalent to 1. Now we calculate their pressure, that is total pressure of the solution. We say P sol we have to calculate. Now if we are going to draw this line, then this line is basically representing what? It is going to represent the vapor pressure of component A, that is solvent. So that is PA it is going to represent, and PA will be equivalent to P naught A XA. So this is a graph which shows that how the vapor pressure of this component is going to change. As you can see that XA amount is going to decrease further, so the PA is also going to be decrease when we move along the axis. Now if you draw one more graph from this point, then from this point if you move backward, then you find that XB is now 1 and XA is 0. So now XA is going to be increased and XB is going to be denoted. So graph for the XB will be denoted as like that. Okay. So this line will represent in the graph the vapor pressure of component PB, which is equivalent to P naught B XB. Okay. So that is how the vapor pressure of two components are represented in this graph. Now we need to calculate the total pressure of the solution for the RAOULT'S law in case of ideal solution. So this line will be our pressure of the solution, which is equivalent to PA plus PB. Okay. So that is how the graph for the ideal solution and their vapor pressure is represented, and that is how we can see how the vapor pressure is going to change. As you can see, component A is going to decrease here, component B is going to decrease here, and in between whatever their vapor pressure is coming, that is the vapor pressure of the solution. So at any point we can calculate the total vapor pressure of the solution. So that is about ideal solution and the graph for the ideal solution. But we all know that there is no ideal thing exist. So there is always a variation from that, there is always a deviation from that. Whenever you are going to prepare a solution, maybe the interaction which is coming is going to be having greater strength or maybe having a weak strength, or the enthalpy of mixing may be something, maybe the volume mixing is also going to be changed. So there is no ideal case exist. So this is the case for the ideal only. But now we are going to see that what are the non-ideal cases and what are the non-ideal solutions. So we are going to see the graph for the non-ideal solution also. That is the graph which are going to show the deviation from the ideal behavior. That deviation may be positive also, may be negative also, that we are going to see. But that is all for today. For about non-ideal solution, we are going to make a new video. That is the next video we are going to discuss about that. So that is all for now. So just watch this, go through this, and then in the next video we are going to discuss further. Okay. So please watch it. Okay. Subscribe my channel and don't forget to press the bell icon. Okay. Bye bye.